Hello everyone. In this video we are going to talk about singular value decomposition, a generalization for eigenvalues and eigenvectors. So if you remember, if we had a square matrix A n by n, I could write it as Q times D times Q transpose, where D was a diagonal matrix with eigenvalues of A and Q was an orthonormal matrix from the eigenvectors of A. And I could do that as long as it has n distinct eigenvectors, which is because either it has n distinct eigenvalues, or if it doesn't have all n eigenvalues distinct, still the eigenvectors could be distinct. For example, maybe A is symmetric. So we talked about that in one of our previous lectures. We called A diagonalizable. So and this was called eigendecomposition. But the question is, when A, in this case M, the same thing, is not a square, so it's m by n and m and n are not the same thing, can I still write such thing? Can I still write it as the product of orthonormal matrices and a diagonal matrix? The answer is yes, and the method is called singular value decomposition. So here I'm going to write m by n as u, which is m by m, times sigma, which is m by n, the same size as the original matrix, and v transpose n by n. And u and v are orthonormal matrices, meaning that U inverse is the same as U transpose, and V inverse is also the same as V transpose. And although matrix sigma is called diagonal, it's not like perfectly diagonal the way we talked about it in the past, because diagonal we refer to square matrices. So when we say diagonal, it's kind of like a pseudo-diagonal. So it is the same size as original matrix M. And let's say here, two different cases, M is bigger than N or M is less than N. If you consider, let's say here it is 4 rows by 3 columns. So sigma is the same as M. So it has these 3 diagonal elements, 1, 1, 2, 2, and 3, 3, that are non-zero values. Everywhere else is 0, or let's say if it is 4 by 5, sigma is the same, and it has again 1, 1, 2, 2, all the way to 4, 4 are non-zero, and everywhere else is 0. So clearly you see the matrix sigma has here an extra row of 0, and here it has an extra column of 0. So it's not like perfectly diagonal square the way we talked about it, but it is very similar to a diagonal element, a matrix. And by the way, these diagonal elements, these non-zero diagonal elements in general, if we show them with sigma 1, sigma 2, and sigma 3, or here we might show them with sigma 1 all the way to sigma 4, these guys are what we call the singular values of matrix M. Okay, so the sigma i's are the singular values of M. Okay, so that's the meaning of singular value. Now, how do we calculate these? Well, we know that for a square matrix we can calculate eigenvalues, but not for rectangular matrices. But the matter of fact is, if I multiply matrix M by the transpose of it and form this matrix called the Gram matrix, M transpose M, this Gram matrix is always a square matrix. So here your M is M by N, and your M transpose is N by M, so the whole product is N by N. So it is a square matrix and it has eigenvalues. Now we can easily show that the eigenvalues of this Gram matrix are what? Are the square of the singular values. Okay, so in this case, let's say for the case of this 4 by 3, your M transpose M is going to be 3 by 3, so it's going to be the same as V. Okay, so this is going to be your M transpose M matrix for this case. And if you can write it as a diagonal, then so if you can write it in terms of Q times D times Q transpose. So if you can find the eigenvalues of it, then this D matrix will have eigenvalues. It's a diagonal matrix with eigenvalues where the eigenvalues are the square of the singular values. Okay, you can easily show that. And because the eigenvalues of it are all positive numbers, it is a square matrix and it is a positive definite matrix. Okay, so that's why we said this is the positive definite square matrix called the Gram matrix. Of course, now the square root of the eigenvalues of that are going to be what? The singular values. So how do I get singular values? I calculate M transpose M. I find the eigenvalues of that, which are in this matrix D, and then the square root of those eigenvalues that are not equal to 0, the non-zero eigenvalues, the square root of them are what? The singular values, sigmas, okay? So that is what you can see here. And also, if you look at the dimension of M transpose M, in this case, you see it's the same as V. In general, it is the same dimension as V. It's N by N. So the columns of V can also be found through what? Through the eigenvectors of this M transpose M. Okay, and that's what you can see here, that the columns of V are eigenvectors of M transpose M. And if you remember, eigenvectors of M transpose M, they are in this matrix Q. So you can say this Q is the same as what? The same as V, not V transpose, the same as V. Okay, and the diagonals on D are the square of these values sigma 1, 2, 3. Right, so you need to get these guys, apply a square root to them, and that will give you the singular values, and this gives you matrix V, as I said, the eigenvectors of M transpose M, or the matrix Q. Now, what about U? Well, U is a different dimension. U is, if you look, U is M by M, while M transpose M was N by N. So in here, we need a matrix that has the same dimension as U, and that is MM transpose. Well, if you look at the dimension of this MM transpose, remember here that your M matrix is M by N and your transpose is N by M. So when you multiply, the result of the whole thing is M by M, which is the same dimension as U. So if you can find the eigenvectors of this MM transpose, those are the columns of U. So the columns of U are coming from eigenvectors of M transpose. So now I know exactly by forming these two matrices, M transpose M and MM transpose, which are of two different dimensions. One is M by M, the other one is N by N. I can get U, I can get V, I can get sigma. And once I have those, that means I have my singular value decomposition. And in MATLAB, the command to do it SVD, or singular value decomposition. You pass to it matrix A, and that will give you U, S, and V based on those instructions that I said. So if I have, let's say, in this case, a something similar to here, a 4 by 3. So let's fill up a 4 by 3 matrix. So 3, 2, 5, 0, 9, negative 1, 6, negative 4, and let's say 8. Okay, so I have this, oh, it's 3 by 3. I need one more. So let's say 1, 4, and negative 7. right? So I have this 4 by 3, and now if I apply this command to it, right? Let me clear my workspace for a second and run it one more time. Here we go. You see that your S matrix, which is the same as sigma in this case, is 4 by 3, the same dimension as A. Your U is 4 by 4, and your V is a 3 by 3, right? So you see that, and you see this matrix is pseudo-diagonal really. These guys here are the singular values of the matrix. These are columns of U, these are columns of V. And you might say, well, what about those commands? Are those eigenvalues and eigenvectors of A transpose A? Well, let's take a look. So here I call my A transpose A, the gram matrix, to be A transpose times A. You see it is a 3 by 3. And now if I use the command eig on it, these are the eigenvalues, and if I apply a square root to the answer, let's see if it does. Yes. Look at the numbers. These are the square root of the eigenvalues of gram matrix, 4, 8, and 14, right? And if you go up here, you see them, 4, 8, and 14. And you can combine them using the command squared of diagonal of D to get you the singular values as well in one single command. So we got the singular values, as we said, through the square roots of non-zero eigenvalues of the gram matrix. Now, if you look at the eigenvectors of that, they should be the columns of V, right? So when we applied this eigenvalue command to the gram matrix G, A transpose A, then it gave me this matrix Q, and the columns of Q are eigenvectors of G. And so these columns should also be the columns of the V matrix. So V was this and Q is this. And if you compare them side by side, if you look at the third column here, you see the third column is the same as first column here, except for a negative one in all of them. The second columns are the same again, except for a negative one. And the third one here in Q and the first one in V are the same, except for a negative one. And you know that for eigenvectors, it's the line of action that matters, and the direction is not as important. So you clearly see that Q gives us the same thing as V is. So that's what I earlier mentioned, that if you apply the eigenvalue decomposition to the gram matrix, right? So you write this M transpose M as Q times D times Q transpose, then the square root of eigenvalues of D will get you the singular values in sigma, and this Q will get you the V matrix. And you see that now that's the case. Now it says the columns of U are eigenvectors of M times M transpose. Okay, so we need to form a matrix which is M times M transpose, and I can call it B to be, in this case, A times A transpose. That is going to be a 4 by 4 matrix. And now if I apply eigenvalue on this guy, two interesting things. One is, if you look at the diagonal entries of the diagonal matrix D for the eigenvalue of this B matrix, one of the eigenvalues is 0, it should be, and the three others, these numbers, if you look at them, they are the same numbers that I got earlier when I applied the eigenvalue command to the gram matrix. If you look at these numbers, 205, 78, and 17, they are the same numbers. So in other words, if I apply that the square root of diag of D, I'll get the same three singular values as well as an extra 0. So basically, not only the eigenvalues the square root of non-zero eigenvalues of M transpose M are singular values, they are also what? They are also the square root of non-zero eigenvalues of M transpose, right? So not only M transpose M, and you can say and, or if you want, let's say or is better, or M times M transpose. The only thing is M times M transpose in this case has an extra eigenvalue which is 0, but we are only interested in non-zero eigenvalues and we are only taking the square root of the non-zero ones. So both of these can give us the singular values, okay? Now if you look at the Q matrix in this case, the Q matrix, the 4x4 Q matrix, the columns of it are eigenvectors of AA transpose, and they should give me the columns of U. So if I compare Q this time to the U that I got from singular value decomposition, if I compare them side by side, you see they are exactly the same. Just look at the first column here. It's the exact same thing as the fourth column here. And then the second column is the same as first column, or the third column. There is a negative 1 difference between them, but again, negative 1 is not changing anything. The third one and the second one are exactly the same. The fourth one and the fourth one are exactly the same. Okay, so you see definitely that here the eigenvectors of AA transpose are giving you the columns of U. Okay, so we have checked all three of these instructions for how to get the matrices U and V as well as the singular values in matrix sigma. Okay, so far so good. Now we have done this, we found U sigma V. Now you might come and ask the million-dollar question, what's the use of that? Fine, I found it. I can now kind of diagonalize a rectangular matrix. Now what? Now it has applications. Like what? Like one of the applications is the pseudo-inverse of a rectangular matrix. If you remember from our previous lectures, when we talked about the inverse of a square matrix, we also said for non-square matrices, rectangulars, we can define something called pseudo-inverse, or more accurately, Moore Penrose pseudo-inverse, and it has a left version and it has a right version, and we showed it with A plus. Let's say the left pseudo-inverse is A transpose times A, the whole thing inverse times A transpose, right? So for example, for our case here, matrix A, if we apply that command, inverse of A transpose times A and the whole thing times A transpose, this is the pseudo-inverse of what? That's the pseudo-inverse of A, correct? This 3x4 matrix. Now, if we want, we can use the singular values to find the pseudo-inverse as well. How? It says the pseudo-inverse of M here, or A, doesn't matter. If M can be written as U sigma V transpose, pseudo-inverse of M can be written as what? V U transpose at the end and then sigma plus in the middle. So first of all, you see that since pseudo-inverse is similar to inverse, when you apply it to a product, it reverses the order. So this is going to be V transpose negative 1. And you know that since it's an orthonormal matrix, V transpose is the same as V negative 1 already. So the inverse of inverse is going to give you V. The inverse of U is the same as transpose of U. So you can see it here. And the inverse of a diagonal matrix, if you remember, if I have a diagonal matrix, completely square, the inverse of that is the same format, diagonal, except the diagonal elements are going to be the reciprocal of their corresponding entries in the other matrix, right? And that's the same thing for sigma and sigma plus. So sigma plus here is the pseudo-inverse of sigma. So what it is very similar to that sigma, but what? As you can see here in this picture, it has the reciprocal of the singular value. So if this is sigma that I have, this 4x3, sigma plus is going to be a 3x4, so it's not just reciprocal of the singular values on the diagonal. It's also the transpose version of that. So what you need is first apply a transpose to sigma. So instead of 4 by 3, you make it a 3 by 4, and then on the diagonals you have reciprocal of these sigmas. That's called sigma plus, okay? So that's what the sigma plus is. And it says, and you can see it here, right? The instruction to get sigma plus from sigma. So it says if you multiply V by sigma plus by U transpose, that also will give you the pseudo-inverse. So we did the pseudo-inverse through that formula by Moore and Penrose. Now let's apply it through the same formula that we have here. So we already have V and U from singular value decomposition, and I have sigma from that. We called it S. So what I need to form is this S plus. So S is what? This. So now I need to transpose it first, and then replace it with what? With the reciprocals. So first I transpose it, and then any entry in it that is on the diagonal, I replace it with 1 over the same thing that it was in S. Okay, so I take the reciprocal. And then I do the same thing for element 2, 2, and then element 3, 3. You see, now the numbers are changing. And now I change the last one, that 4.20. I change that as well, and there we go. So now that SP is the sigma plus, and now I can say that what I need is V times the sigma plus times U transpose. This is also the pseudo-inverse, and if I compare it with the previous pseudo-inverse side by side, you see they are identical. Look at them. This is what we have through this new formula. This is what we had through the definition by Moore and Penrose, right? So one application is you can find the pseudo-inverse. And you might say, well, I had already one formula. What's the use of this? Well, this is more numerically stable, because what MATLAB does when it calculates these pseudo-inverses or eigenvalues, singular values, and so on, they are all done numerically. It's not doing anything by, let's say, when it finds to find eigenvalues, it's not going to form the characteristic equation nth order and try to solve it analytically. Most of the time, there is no analytic solution. So it does all of that numerically, and numerical methods, they have their own issues. They have stability problems, convergence problems, accuracy problems, and so on. And it turns out if you calculate the pseudo-inverse this way, it is actually quite more accurate and maybe even faster than that Moore Penrose formula. But that's not the only application. The other applications is, and by the way, just as a reminder, where would you use this pseudo-inverse? You might say, well, fine, I find the pseudo-inverse of a matrix. Now, where would I use it in real life? If you look at one of our videos called List Squares Curve Fitting, you'll see this is the place that you use it. So if you have a linear set of equations like x equals b, but the set of equations is overdetermined. So a is like m by n, x is n by 1, and b is m by 1. So you have n unknowns and m equations, but m is bigger than n. So you have more equations than unknowns. Okay, and there will be never any exact solution here. You can just find a solution that minimizes the square of the error term, where error here is defined as a times x minus b. Ideally, this should be equal to 0, right? Because if you determine x is such that ax equal b, then if you bring b to the left side, the difference between left and right should be 0. But since you can never find exact solution, there will be this term that is non-zero. So what you do, you square these terms for each and every one of the variables, add them together, and try to find the solution x that minimizes the square of this error, sum of the square errors. We call it list squares curve fitting. Okay, and in that case, if you watch that video, you'll see that the solution, a list squares solution of x, is equal to a pseudo-inverse times b. Okay, so that's one of the places, because this A matrix is not, you cannot invert it and multiply it by B. It's not a square matrix, but you can apply the pseudo-inverse of that times B, okay? So one of the places you use pseudo-inverse is least square curve fitting, and you can use this formula to calculate it. And it's also the calculation of the rank. If you remember, we said rank is the number of linearly independent rows of the matrix. And the way that we calculated the rank was through elementary row operations and what we call the Gaussian elimination. And then we looked at the number of rows at the bottom of the matrix, which have all of the entries equal to 0. Right? If we don't have any, we say the matrix is full rank. If we have a few or even one, we say the matrix is rank deficient or singular, right? So that was one way to do it. Another way to do it is we can look at the singular values of the matrix. The number of non-zero singular values of matrix, so the number of non-zero sigmas is the same as rank for M. Okay, so rank is the number of non-zero singular values. And actually, when you use the command rank in MATLAB, that's how MATLAB is calculating it. It doesn't do the elementary row operations. It might not be as fast, but definitely it is more accurate. And I can show you here. So if you look at the sigma matrix for A here, it has three singular values that are non-zero. So the rank of A should be 3. And if I use the command rank, you see these 3. Okay, but if I had a rank deficient matrix, then rank would be less than that. So let's say here, if I change A, so A was this, right? Now, if I go ahead and change A a little bit, and let's say make the 4th column to be different, linearly depending on one of the columns. So let's say here, I make, let's say, the 3rd column maybe twice as much as the 1st column, so it's 6, 4, and then 10. So now clearly your 3rd column is 2 times the 1st column, right? And now this guy should not have full rank, so if I run rank A on it, you see it is still rank 3. Now, is that correct? Because if you remember, it's the number of independent rows. And this guy already has 4 rows, but the max rank it can have is the minimum between 3 and 4, which is the number of rows and columns. So it is still okay, right? It still has 3 independent rows. Oh, yes. So I need to change it a little bit more. So this is good. This is good. This is good, but the last row, I make it to be, let's say, the 1st row plus the 2nd row. So now I make it 3, 11, and 4. Now, definitely the 4th row is not also linearly independent. So now rank of A should drop to 2. And you see it does. Now, if I apply the singular value command on this new A, and you look at your singular value matrix sigma, you see that one of the it has, if you remember, it has 3 it had 3 non-zero singular values. Now one of them is what? 0. It only has 2 non-zeros, which is the same as what? Rank of 2. Okay, so this is another application. And another good application that you might see a lot in image processing, machine learning, and so on and so forth is data compression and reduction in the size of data. Okay, and what do I mean by that? Well, in data compression, let's say if you have an image, Okay, so you have an image. Let's say this image is 500 pixels by 360 pixels. So this is definitely a matrix, right? And if you apply the singular value for it, so say A is equal to what? Equal to U times sigma times V transpose. The size of this sigma is the same as A, so it is going to be 360 by 500. And it will have a maximum of 360 singular values. Now, the matter of fact is the singular values are not all the same magnitude or similar magnitude. Some of them are way bigger than the others, and you can show that the ones that carry the larger numbers, the singular values that are larger, are the ones that carry most of the information and the characteristics of the image. So if out of these 360 singular values, you just neglect a bunch of them that are very small, they do not carry so much of information. So you can just eliminate them, right? So instead of considering the sigma to be 360 rows, right? If you look at the magnitudes of the sigmas, so this is sigma versus sigma number, you see some of them are very large, but they drop very fast. Okay, so if I have like 360 singular values here, the matter of fact is not all of them carry the same weight. So maybe after, let's say, 100, 50, 60, 200 or so, they are really minimal contributors and I can get rid of them. And get rid of them means I can consider them to be zero, and if they are zero, I don't need to save them in the memory. So that way I can reduce a lot of rows or columns in sigma, U, and V, and that means data compression. So now to demonstrate that to you, I wrote a simple code here. I downloaded one of the famous image processing pictures called Lena, and converted it to grayscale, converted it to double so I can apply the command singular value decomposition to it. I'm looking at the diagonal entries of it. By the way, this matrix is 489 by 372, so I have 372 singular values. And instead of me looking at each sigma, I'm gonna look at the cumulative sigmas. So basically, summation of sigmas from the first one to the current one and plot it versus the sigma number. So this shows the cumulative effect. And if I do that, just this portion of it, this is the cumulative, okay? So, and I normalized it. So this is not really sum of the sigma, this is sum of the sigmas, but normalized. So it's like 1 here means 100% of information or energy stored in your signal, in your image here. So if you look, although I have 370 something pixels, but really if I want to look at, let's say, all I care is only the top 90% of the information. 10% of the information I can just throw away without losing a ton of image quality. So if I look using data cursor, where is it? At what singular value do I have 90% of the image information stored? If you see here, it is about 123. So I do not really need 372 singular values. As long as I can only use 123 singular values, that means I have 90% of the information in the image captured. And so now I can go and use a cutoff here. I use here a very low cutoff, but if I say 123 singular values, keep the rest of them set to 0 because they are not contributing too much. They are together, all of them, the rest of the singular values, which is 372 minus 123, which is about 260, is 260, which is 2/3 of the data, or more than 2/3 of the data, only providing 10% of the info in the image. This 1/3 of the data is providing 90% of the info in the image. So I would rather just keep this first 1/3 true, the rest of them to 0, and then I use this new sigma matrix, which only kept 123 of them, the rest of them set to 0. And then this compressed version of the image, a new, I'm going to show side by side with the original image. So if you look here, this is the original image on the top. This is the compressed image on the bottom. And you can barely find any visual difference, right? If I show them in big scale, you probably see it a little bit better, but clearly you see that there is not so much of a big difference. So here I can change the way they are set next to each other, right? And let me add some title, right? When you create some plot or picture, it's always good to provide the viewers with some useful data, labels, tags, and so on. So now if I put them side by side like this, clearly you see, if you look at here in this image, you see that the texture is losing its quality, which are really high frequencies here. There are some very fine texture here. Or maybe you can see a little bit here over the hair, but the rest of it is not really majorly affected. So I just kept 1/3 of the size of the sigma, and the rest of it I set to 0. Now I can go even further down. So I can say, well, I don't want 90%, maybe I just only want 80% of the data, right? And if you look here, it is roughly at 65, right? So I reduce it, the size of the number of sigmas to keep, by 1/2 again. And if I do it this time, you definitely will see some distortions, because only 80% is now conserved. Right, you definitely see the pixelations here and everything, but still you can easily recognize the main subject. Okay, and this is one of the ways that you can compress an image, and that's one of the ways that they try to reduce the size of the data for acquiring meaningful, higher level labels, information, and so on in machine learning and computer vision. So hopefully this lecture on singular value decomposition was useful to you, and you learned some applications for it in real life, and I will see you in my next video. Thank you.